Introducing Qualities of Software Engineering by Team Nooglers.
Verifiability keeps the critical systems, such as medical devices and autonomous vehicles, safe. It avoids catastrophic failures by continuously validating updates. SAFA works in two ways. It maps system artifacts to identify safety gaps, while its trace-link generation is automated to ensure changes are compliant with safety standards. A major challenge is the big freeze, when development stops due to safety concerns. SAFA solves this by detecting and showing safety impacts so teams can act quickly. Compared to Doors and Jira, SAFA offers more automation and real-time visualizations, reducing manual effort and speeding up analysis. SAFA works best in Agile or DevOps environments, where frequent updates require constant safety validation. SAFA's accuracy depends on data quality. It may struggle with large projects and setup requires fine-tuning. I chose this paper because it shows how SAFA improves verifiability by automation, and that was something I wanted to explore. What were you hoping to learn? I wanted to see how tools like SAFA balance safety compliance and fast development. They believe SAFA works because deep learning generates trace links to lower manual effort and provide quick safety insights. I agree. Automation of safety analysis saves time and makes sure continuous compliance is guaranteed within evolving systems. Are the conclusions logical? The results are logical, well-substantiated, and present how SAFA contributes to the mitigation of safety risks in dynamic projects.
Performance is important because it can impact user satisfaction, operational costs, and the stability of other software. Users can get annoyed if a program is slow or laggy. Operational costs, like electricity, could increase if inefficient software is run on local servers. And the stability of other programs dependent on poorly performing software could be at risk due to slow processing times. This paper covered two methods of performance testing: field operational data analysis and development phase analysis. Field operation data analysis relies on collecting data from users and analyzing it with a black box machine learning model to pinpoint any areas that have a lower performance than before. Development phase analysis is about running tests on specific components instead of the entire system and analyzing it to spot any performance regressions before release. These methods address common issues related to performance testing like resource and time constraints. Since large-scale tests are not run before deployment, valuable time is saved, and by offloading testing to users, less resources are required. These testing methods work best with software that is frequently updated, so any performance issues detected can be resolved quickly. The first method has the limitation of needing readily available user data to analyze. I chose this paper because I was interested in how developers prevent the performance of their products from degrading over time, especially if it is a project that constantly adds new features on top of old ones. I was hoping to learn what performance testing methods are effective and how well they work. The authors think their methods work well when compared to other performance tests because they analyze real-world data and don't need to run expensive large-scale tests. I agree with the author's viewpoint because not many resources are spent collecting the user data, and the data collected is going to be more accurate than any simulated testing can provide. I think their conclusion is logical because they tested both methods in real projects and analyzed the results. Bug Listener is important. It really boosts software reliability by automating bug tracking directly from chat conversations, which helps catch issues that might otherwise get lost in busy, ongoing discussions. In practice, Bug Listener monitors developer chats, separates mixed-up conversations, and automatically generates structured bug reports, saving time and reducing the risk of missing important details. It's especially useful in collaborative environments where there's a lot of noise and back and forth in chats. Bug Listener is ideal for open source or remote teams who rely on chat tools like Slack. It has some flaws, though. It depends on chat data, so it may misclassify things like user errors or struggle with sparse feedback. But unlike traditional methods, Bug Listener uniquely automates bug reports directly from chats, setting it apart from techniques like pair programming or automated testing. I chose this paper because it focuses on using machine learning to create a practical, useful tool. I was interested in how machine learning could manage unstructured chat data to improve software quality. The authors think Bug Listener works well because of its layered approach. It separates conversations, uses neural networks to understand the context, and applies transfer learning to make sure the documentation is accurate. I agree with the author's viewpoint. Bug Listener genuinely enhances reliability by automating the documentation of bugs right from the chat, which is pretty unique. The conclusions they make seem logical and are backed by solid results, although it'd be great to see it tested in more varied settings. In this presentation, I'll discuss Preach, a tool designed to tackle one of software testing's biggest challenges: reaching and evaluating hard-to-access statements often missed by traditional methods. This capability is critical for ensuring software quality, particularly in safety-critical applications. In practice, Preach is used in software verification competitions and large-scale projects to classify statements based on reachability probability, helping developers focus on genuinely hard-to-reach code paths. By addressing the path explosion issue, where program paths increase exponentially, Preach offers a scalable solution. Unlike traditional probabilistic symbolic execution, which struggles with path explosion, Preach uses branch selectivity and Markov chains, allowing it to handle deeper and more complex paths efficiently. Preach is ideal in settings where scalability and handling deep execution paths are crucial, such as in automated testing for large projects or software verification benchmarks. However, it has limitations. It relies on heuristics rather than precise analysis, which may lead to approximations rather than exact results in complex cases. I selected this paper because it presents a novel solution to a long-standing problem, demonstrating how probabilistic methods can make testing more efficient. The authors argue that focusing on branches rather than full paths enhances scalability, and I agree with this viewpoint. Their conclusions are well supported, showing Preach's potential to improve software testing by making deep and complex paths more accessible and manageable.
Correctness in software is about ensuring a program functions as intended. It is an absolute quality, meaning any deviation from expected behavior signifies failure. It's crucial because any deviation can undermine user trust, incur costs, or even pose serious risks. Maintaining correctness is especially vital for software where errors could lead to significant consequences, from financial losses to user safety issues. This study is designed to address a core aspect of software quality, detecting and preventing defects early. By combining real-time data on developer behavior and physical responses with traditional code metrics, this approach aims to predict when bugs are likely to occur. We hope to learn if this integration could enhance strategies to sustain software correctness and proactively catch issues. The study focuses on a developer-centric approach that monitors real-time physiological metrics, such as stress and focus levels, to gauge when a developer might be more error-prone. This data can be used to create supportive tools, boosting developer productivity and well-being by addressing potential errors as they arise. Unlike traditional methods that rely on static code metrics, this hybrid model incorporates live data from developers. It goes beyond lines of code or fault rates to include human-centered factors, which could enhance the accuracy of defect prediction. It's important to note that the developer-based model alone had 3% lower accuracy than the traditional code-based approach. Their hybrid model, consisting of the developer-based and code-based approach, achieved an accuracy rate of 84%, outperforming code-based analysis alone by 5%. This reinforces the value of integrating developer-based and code-based metrics for more reliable defect prediction. This technique is ideal for teams that value high-quality code and can implement non-invasive monitoring. The approach is most effective where developers are open to activity tracking, adding depth to quality assurance practices. However, privacy concerns and discomfort with biometric tracking are notable limitations. Additionally, using wearable sensors across teams may not be practical due to cost and environmental factors that impact data reliability. Thus, a hybrid approach combining both behavioral and code metrics provides the best outcomes.